So, hello everyone. My name's Alexander Bell. I'm a data scientist working for a company, consulting company, Integral Concepts, based out in Michigan. And today I'm going to talk to you about using artificial intelligence to detect imminent failure in complex systems like automobiles. So I'm going to go ahead and set up my screen share. So just take me a second. Okay, I think, does this look okay, Fred? I mean, if anyone's got issues, then I assume they can like say in the chat, and then if we have to, we can try and fix that. But you should be seeing my title slide on the screen now.
Yeah, we got it, X. We got it.
Good. Okay, so yeah, so this is the company that I work for, Integral Concepts, a logo. And yeah, as mentioned, today I'm going to talk about using artificial intelligence to assess imminent failure and causes of failure for complex systems like cars. Okay, so to begin with, I thought it'd be good to kind of just give you the overview of what we're going to do here, and then I'll go into the kind of the presentation of the structure of this presentation. So what I'm going to do is what we're going to do here is we're going to use data on automobiles and give that into an AI model, which is then going to determine whether or not that automobile is okay, at least for the near future, or if that automobile is at risk of imminent failure. So I'm going to explain more thoroughly what the problem is, but this is what we call a binary classification problem. The specific type of AI model that I'm going to discuss in this presentation is called a decision tree. So I've got a little illustration of a decision tree, and later on I'll discuss that. I'll explain that in a bit more detail. And in addition to developing this model to be able to detect whether a car is okay or if it's at risk of imminent failure, we're also going to look at how, when you examine the model, you can discover why a car might be at risk of failure. So we'll understand how is the model telling the difference between these two types of vehicle. So the structure for this presentation, the way I've chosen to present this is as follows. First of all, I'm going to talk about the problem. So there we're going to discuss a bit about automobiles. I'm going to discuss a bit about classification specifically as a machine learning problem. And I'm going to spend a lot of time kind of explaining how you might go about collecting data in the right way to be able to apply machine learning to this problem. In the second phase, then, I'm going to talk a bit about artificial intelligence and machine learning. I just want to make sure that the way that I'm using these terms is clear. And then I'm going to specifically talk about decision trees, which is the type of algorithm that we're going to use for this classification problem. In the final phase of the webinar, I'm going to look at applying the tools that we talk in the middle phase to the problem of classifying automobiles with respect to imminent failure. So I've got an example data set that I put together to demonstrate the application of this tool. And specifically, there's an algorithm called CART, C-A-R-T. This stands for Classification and Regression Trees, which has been implemented in Minitab. And so I'm going to illustrate with some pictures how you apply decision trees and CART in Minitab. Okay, so to begin with, I'm going to talk a bit about automobiles. So I'm not an expert in automobiles, but I can understand that they're very complex systems. So to me, when I say complex system here, I mean it has a lot of different parts to it. And so there's a lot of different ways that an automobile could fail, and there's a lot of different pathways to failure. So in order to facilitate illustrating how you could apply machine learning to this kind of problem, I'm going to make a couple of simplifying assumptions. First of all, I'm only really going to focus on the engine of the automobile. So when I say system failure here, really I'm talking about engine failure and the different ways that the engine fails. So I'm ignoring what you could argue are other kinds of fail modes like issues with the wheels or something else. I'm really just going to focus on engine failure. And then another big simplifying assumption or decision that I've made here is I'm only going to look at the first failure post-production for units. So I'm not going to consider repairable systems. I'm only looking at the first failure after a unit's been produced. So I'm going to talk a bit about now how you could imagine data might be recorded for a system such as an automobile. So we can imagine that a car could have a series of onboard sensors that records data from the unit. So it could record things like average speeds, maximum speeds, oil levels, airflow, etc. Now, I'm going to imagine the data is recorded at regular time points. So I'm going to use a little bit of math in this presentation, but the math isn't super important here, other than just to express these ideas. So I imagine that there's an initial point T naught, let's say, when the unit's produced. We don't necessarily have any data there, but at regular points afterwards, at regular points in time, data is being recorded from all of these sensors. So you can imagine data is being generated and it could be stored on board on the vehicle with its electronics and or communicated to external sites. So I know certain companies like Tesla have wireless connections with their vehicles and are able to do wireless updates. So in the bottom right here, I'm illustrating a typical data table or spreadsheet, where we have the variables as the columns and the rows are instances of data. So the first column could be the time points. And throughout the presentation, I'm going to use this capital X sub a number, which just represents something we're measuring. So this could be temperature, speed, airflow, etc. So these are just rows of data from different points in time. And just briefly, I'm not going to delve too much into the real details of this problem, something we could perhaps discuss at the end. Because again, I'm not an expert in automobiles, but I think practically you can imagine that there might be data being recorded on a minute by minute basis, and then that data would be averaged, and these actual points would be daily averages, for example. I think that would make more sense. But that depends on the granularity on how it's set up to record data. So now I'm going to talk about the classification approach. So there are multiple ways that you can define problems in machine learning, and there are multiple different algorithms that match up with those problems. For simplicity and brevity, I'm going to talk about just one of them really in this webinar, and that's classification. So, and specifically, I'm going to be doing binary classification. So here we're going to assume that there's two species of car, if you like, two species of automobile. And we'll use the term classes. So one kind of car is one that is likely to fail soon. So there's a high probability that it's going to fail within a certain period of time. And I'll discuss that time element in a sec. And then the second type of car is a kind of car that isn't likely to fail soon. It seems to be okay, at least for the time being. So the idea is that, we have a lot of automobiles, we have a lot of cars, but there's two types of car, and we're going to try and identify and understand how can we get data that represents these types of vehicles. So when I use the term imminent here, when I'm talking about, it's going to fail soon, I'm going to assume this means within a fixed future period of time. So for example, within the next 3 days. But that's variable depending on how you'd want to design this, if you want to predict a week in the future. And also it's debatable. I think you'd study whether or not there's a signal in terms of being able to predict failure at certain points in time. But again, for a simplifying assumption, I'm just going to mean within the next few days or the next period of time. As mentioned already, I'm going to assume that the unit was produced at some point at a time T naught. And then we're going to be developing this model at some later time. So I'm just going to use the subscript T sub now. So then a key question then is how do we obtain data representing these classes? And I should also make it clear, I put it in brackets there, that from now on I'm going to refer to classes like cars that are likely to fail soon simply as fail, and the cars that are the negation, that where failure is unlikely, is simply okay. So we have fail and okay automobiles. So to begin with, I'm going to think about and discuss with you how could we obtain data for failed units or units that are imminently going to fail. So the picture for that unit looks something like this. So I've kind of illustrated the timeline on the right here. So you have the time the unit was produced, T naught on the left, and you have the time that it is now. There's been data being recorded at regular intervals, and at some point the unit failed. And I think I have annotations. So you have the actual failure time, T sub capital F. It failed at some point. This is highly unlikely to be a point at which data has been recorded. But then you have a closest point at which the data, a daily average, for example, has been recorded. And I just used the lowercase f there. So the idea then is we want to find, a point of data that's close to the point at which it failed in order to represent a kind of vehicle that is imminently going to fail. So for simplicity here, I'm going to use this t sub f minus I, which basically it just means I'm going to select a previous time point to represent that. The question, of course, is, well, what is the I that you choose? How far back in time do you want to take that data? And that really depends on your definition of imminent. But when you have then determined how many days, for example, you want to get before the actual failure point, this can then give you a row of data for a data table that represents a fail class. So, as mentioned already when I introduced this table, this just represents typical spreadsheets. You have time as a column. You have these X of J features, which are just characteristics you measure, such as temperature. And then you also have a variable, which is a binary variable, which is the class. And here I'm illustrated one way you could obtain data for the failure class. So the other kind of unit then of units that haven't failed. So the picture is quite simple. It simply just has data recorded up until the point now where we're developing a model. So a less trivial kind of situation then or question here is, what time point should we be using to represent a vehicle that isn't likely to fail soon? So you can imagine we have quite a bit of choice here. So I'm going to present a solution to this. I don't know if it's like the perfect solution, but I do think it's sufficient for the illustration that I'm presenting here. So consider that we're going to be comparing these units that haven't failed yet to the ones that are going to fail. So the idea then that I'd propose is that you consider the average time of the failed units. So you have this timeline for a unit that hasn't failed. It has data recorded at regular intervals. And then all these little red X's you can imagine represents the times of units that have failed. Then there's going to be a mean failure time for the vehicles that failed. And then there's going to be some closest point of time. So I've just used like a little asterisk or star here for a unit that hasn't failed to the average point at which the units have failed. And yes, I have annotations here where you have the average of the failure times. And again, you have a closest recorded data point. Now, note by doing this, it's highly likely that the point at which you'd record data for a unit that hasn't failed is significantly less than the current time t sub now, which is really ideal because however you select data to represent a car that's not about to fail, you don't really want to use data, I believe, that's close to the current time because for all you know, it could be about to fail. So we avoid unknown fail cases. And so this illustrates then how you might obtain a row of data in your table for an OK class. So you can use this starred time here, which is close to the average failure time. You know that it isn't close to the current time. And so this is, I think, a good way of getting data that represents an automobile, for example, that isn't going to fail soon. And then you have measurements for all these features on that point in data, on that time. So now we've discussed how you can obtain data for those two different types of classes. I'm going to discuss a bit about the kind of the problem setup from a machine learning perspective. So we have data collected at the current time for these two classes. The table would look something like this. So you have the IDs of the units. So just something that identifies the cars, for example. You have the time points at which data has been collected based on those previously described schemes. You have a number of features like speed, temperature, etc., that have been recorded for those time points, and then you have these two classes, OK and fail. So what we're going to do, and what I'm going to kind of illustrate here, is the idea that of training an AI model that's going to learn how to tell the difference between these two classes. It's going to take this data that we've formulated here. We're going to tell it essentially that there are two classes, and we want to be able to determine the difference between those two classes. Okay, so now I've discussed the setup, the problem. Um, I'm now going to talk about the kind of tool that we can use to solve the problem. So I'm going to move on to kind of discussing AI and machine learning and then decision trees. So to begin with, I want to talk about artificial intelligence. So this is a topic that's been extremely popular lately. I'm in San Francisco at the moment, and you can see AI billboards and advertising everywhere. So, it's obviously something that's really kind of taking the world by storm. But I want to be clear on my use of the term of AI. So to me, artificial intelligence, it's a branch of computer science. So computer science being what we can do with computers, and specifically, it's that branch which mimics human intelligence and reasoning using machines. So I have a funny little kind of illustration here. So one thing that we do that's intelligent as human beings is that we see objects in the world. We receive information, for example, light to our retina, which is then transmitted to our brain. Intelligence and reasoning goes on in our brain, and then we're able to perform a task like classification, where we recognize what the object is. So we take information and we connect it with a discrete class. In this case, you see a bird, you recognize that it's a bird. So with machine learning, with artificial, sorry, not machine learning, with artificial intelligence, you're essentially trying to do these same kind of things, but using machines. So the machine receives information. This is my illustration of a webcam here. This information is transmitted to the computer. It does the same kind of intelligence. Well, it does what, we're trying to mimic intelligence and reasoning we do with our brains on the computer. And then it's able to do the same kind of task, such as classification. So it can see and recognize objects, for example. So this is one kind of intelligent activity that we do with our brains. So now I want to kind of describe a machine learning and just be very clear on what that is. So I've said AI is a branch of computer science. Machine learning is a branch of AI. So artificial intelligence, as I've described it, you don't need learning in order to be able to do it. And you don't need to use data to generate things to do it. You could just use logic, write a program, knowing certain inputs and outputs. So a human, a software developer engineer, creates a program in order to get a machine to do something like classification, to act intelligently. So AI in general isn't all machine learning, but machine learning is a subset of AI. The major thing that defines machine learning is data. So machine learning uses data and algorithms based on the idea that you're taking data in order to create models that perform artificially intelligent tasks like classification that allow computers to make decisions. And it does this really by looking for patterns and fitting models to data. So machine learning is all about data. There's a lot of different ideas and methods that exist within machine learning. Decision trees is one of them, and that's the one that I'm going to focus on in this webinar. But I've kind of illustrated here also regression, nearest neighbors, and clustering, just FYI. And I think, given the popularity of things like ChatGPT, I want to mention that deep learning is a subset of machine learning. So it's a particular kind of machine learning algorithm, meaning that it's based on data. It uses data to determine its model and to do these intelligent tasks. But it uses a device called a neural network. Um, and examples of algorithms based on deep learning are things like large language models, LLMs, like ChatGPT. Now, I'm not going to say anything more about that in this webinar. The focus is, I think if you can see my cursor, decision trees. But I just wanted to kind of convey that kind of connection. Okay, so I'm going to talk quickly about machine learning problem and algorithm types so you can understand the specific problem that we're looking at here in this webinar. So all problems in machine learning are kind of divided into two major camps. That's supervised and unsupervised. The difference between them is whether or not you are using the true output of data in creating the model. So supervised, which is, I think, arguably the more popular and widely used form of machine learning, uses data where you have a set of known outcomes. So you know the true outcome, the true target. So in our case, for example, we know which cars are okay and which cars are about to fail. So what we're going to do is a supervised exercise. And you use that, the algorithm knows this and uses this to try and find the best model it can to determine the difference between classes, for example, or to predict a number. I'll mention briefly that unsupervised is another major area of machine learning. So in this case, there is no target. There's no truth. There's no thing that you're trying to tell the difference between per se. In unsupervised learning, you're just looking for significant features within the data, one of which is clustering, where you're looking for notable groups and differences between points within data. So I'm not going to talk too much more about that because, yeah, our focus will be on supervised learning. Supervised learning is further split into classification and regression. These tasks, these terms are defined entirely by the target of the problem or the algorithm. So we're doing classification, and here the target is a class. It's a discrete label or output. In our case, it's binary. It's just okay or fail. Now, this is a little point of confusion, perhaps. I've given an example of logistic regression. So logistic regression is typically used to predict a label response, so like nominal regression or binary logistic regression. From a statistical perspective, I think regression refers to computing coefficients in a model like this. But in machine learning, regression has a different meaning, which I'll discuss in a sec. When you take that final step in logistic regression, where you go from a probability to an actual class, that would make it essentially a classification model. In regression, in regression learning, the target is a number. It's a numerical value. So this is different to classification. And a typical simple example I think most people will know here is like linear regression or multiple regression. So you're predicting a number. Another important concept to understand, and you'll see this a bit in the application, is training and testing. Um, so supervised machine learning generally follows a kind of two-phased approach. More complex algorithms will involve more steps, but this basic idea really applies to pretty much any algorithm in machine learning. The first phase is that you train the algorithm. So you have a large sample of data and you build a model based on that data. But then an important second step is testing. So in testing, you estimate how good the model is using, and I really stress this, an independent sample of data, independent test data. So we usually call this training data and test data. So what often happens in machine learning is you have a total amount of data and you use most of the data usually for training, 80, 90% of the data, but you keep some data separate and you don't use that to train the model so that you can test the model. What you don't want to do, and I've seen this, I've been an academic recently and I researched at the University of Michigan for many years. You never want to use training data to test a model. The model as it's developed in machine learning will do the best it possibly can on the training data. And so it usually provides an extremely optimistic and biased, an incredibly biased estimate of how good the model is. So the reality is, if you have a model that looks really good on training data, that does not mean that it's a good model in general. And it's quite easy to give an example of a model that has really good accuracy on training data or even perfect accuracy, but in a random test is completely terrible. So yeah, I could discuss more on that later if people are interested. So now I'm going to talk about the specific algorithm. So this is a supervised machine learning algorithm and a classification. I'm going to talk about the classification version of it that I'm going to apply and illustrate in this webinar, and that's decision trees. So decision trees are a way of thinking about attacking this problem from a divide and conquer perspective. So that's kind of key. I think the terms divide and conquer are important to have in mind for understanding decision trees. So I'm just going to kind of walk through the steps. You imagine to begin with, you have all of the training data, all of the data you're going to use to build the model. And then what we'll do is check each variable that we want to use for predicting an outcome. And we're going to use that variable to split the data into subsets. So I have a little simple illustration here. In the top right, you'll see two classes, circles and triangles, let's say. And don't worry about the axes meaning anything. The axes don't mean anything in this. I'm just going to show the idea of splitting. And let's suppose that for each point we have like something measured with x sub 1. Okay, so we have various things measured for these points. And what you do is you compare the variable to a specific value, a threshold. And by doing this, you split the data. What we're going to do then is with this algorithm is that you are looking for the best splits. And the term best here means producing the purest subsets. So there's kind of a lot of detail, like the technical details can get kind of complicated. I'm going to talk very simply about this. And you can assume like pure means mostly one class. So as we split the data into subsets, we want to try and isolate the classes. So for example, let's suppose that some measurement is equal to or greater than a value isolates four of the points that are triangles. This is a completely pure class. So this is something that we ideally want. Because then it's clear at that point that you've been able to, if one measurement is greater than some threshold, you've completely isolated the class. You know what the outcome is. The other kind, if this is completely pure, this is a very mixed group here. So on the left, you have a lot of circles and a lot of triangles. It's not clear what you would say is likely to be the outcome in this group. Then, given this criteria that we're looking for the best splits, you find the best split and then you apply this idea recursively. So you keep applying it down the tree until you hit some stopping criteria. So for example, let's imagine you could find another feature that you test here with a threshold that further splits the data. And then we could obtain relatively pure subsets of data here. So mostly circles, mostly triangles, and that might be a point at which you stop the algorithm. There's a couple of different ways you can define stopping criteria for decision trees. It could be when there's completely pure nodes like this, although that often produces very complex or overly complicated trees. It could also be based on how many terminal points or terminal subsets that you will allow. So there's a lot more detail I can go into, but for the sake of this webinar, I just wanted to get the general idea across that we're splitting the data into subsets and trying to find pure subsets, as pure subsets as we can, as quickly as we can, so that you can say, well, taking this data, if this variable is greater than this, then it's a triangle. Otherwise, you do some other activities, and then you find that it's a circle or a triangle. It will lead to as high a likelihood of a single class as you can. So I will now talk briefly about the specific algorithm that implements decision trees that I'll be using in Minitab. So I mentioned it, I think, when talking about the presentational structure. So the algorithm is called CART. CART stands for classification and regression trees. So this is an algorithm that implements decision tree learning. Um, I have an illustration of the book or the paper here on the left. So it was published in 1984 in the US. It's been cited over 70,000 times. It's extremely popular in the world of machine learning. And the authors are pretty popular. I just mentioned a couple of them uh, and their associated work. So Breeman is known for working on and introducing random forest, which is a very popular algorithm in the world of machine learning. And Jerome Friedman, who I believe is at Stanford Mathematics, so even not very far away from here in San Francisco, he's developed algorithms called MARS, which is, I'll just say the RS is regression spline, so it's a very powerful general regression method, as well as TreeNet, which is a powerful gradient descent method using trees. And all of these algorithms, and I'll mention it again briefly at the end, I think, are implemented in Minitab. Okay, so now I've discussed the tool in detail. I've discussed decision trees and machine learning, and we discussed the problem of the automobile problem. We're going to go back to that data set of automobiles that are okay or imminently going to fail, and I'll illustrate just using images how you can apply CART to this classification problem. So I've created a demonstrative data set to kind of illustrate how this might work in practice. So I imagine you have data on, say, 500 vehicles. 373 are of the OK class and 127 of the fail class. So we have a good mixture of OK and failed cases. And then let's imagine that we measure 8 different variables or 8 inputs. So this is a screenshot from Minitab. So as introduced previously, you can imagine you have the first variable is the ID of the unit. So in this case, it could be an automobile ID. And then we have variables recording data on, and I can just go through temperature in Fahrenheit, the oil level of the car, the RPM in the engine, the tire pressure, sound coming from the engine compartment, maximum and average speed. Again, this could be a daily average, airflow in gallons per second, and then finally the class. And again, recall this is a supervised learning problem. So because of how we collected the data, we know what we consider to be the true class. We know that these are either cars that aren't going to fail soon or cars that do fail soon. So this was what makes this a supervised binary classification problem. And yeah, so the instances, the rows here, like how do you get these rows of data? That's what the first part of this webinar was largely about. I was kind of describing a way in which you would collect and put together a data set like this. Okay, so I'm going to use Minitab to illustrate the application of decision tree with CART. So Minitab has a predictive analytics module, which is an add-on to the standard Minitab statistical software. You can see the variety of predict PA algorithms here. You can see linear regression, logistic regression, random forests, TreeNet, and Mars, which I mentioned briefly with the authors in the previous slides. In this example, I'm going to look just at CART classification. So I'm going to use a decision tree for classification. I'm not going to go through all of the options here. I'm just going to illustrate the kind of major decisions. So this is a binary response. The response variable is just class from the previous one. It's an OK or a fail. For the sake of this tree, I don't think the actual response event is that important. It could be OK or fail. I think it really just determines the coloring, perhaps, that they use in the tree. You'll see that in a sec. And then I'm going to use all of those 8 features as continuous predictors. So this is the kind of output that you get from applying CART to a set of data. So I hope you can see it okay. So I'm just going to discuss a few of the features of this. Each of the boxes that you see here is called a node, and this represents a kind of a set of data, basically. The very top node is the entire data set. So you can see about 75% of the data here are of the OK class, about 25% of the fail class. I apologize if the text is really small or hard to read. I think the slides will be shared after this, so you'll be able to kind of look at it in detail then if you like. But this is the whole data, and then as mentioned, what the algorithm does is it tests every single variable and every single value between the data that we have for that variable to use as a threshold, and it finds the one that gives you the most pure on average outcome at that point. So you can then see two lines coming out of this, and this is splitting the data into two subsets, and then we have two more nodes here. I'll read off that this is the temperature in the engine if it's equal to or less than about 215 degrees Fahrenheit. Then we have a set of data here, which is most of the data. I think it's about 360 points in all. And you can see that most of this data is of the OK class. So if the temperature isn't super hot, then about 90% of the data is a car that isn't going to fail soon. Whereas if the temperature is greater than, say, 215 Fahrenheit, then you have this set of data here, which is about 70% fail vehicles and 30% okay. So neither of these are perfectly pure, but this is a very pure node, and this is relatively pure with respect to fail. And so the algorithm, when checking each possibility, found that this is the best in terms of having maximum average purity. And then the process repeats, it iterates. So now for each node, it's going to be split again. It looks for the best variable, and it keeps doing this until it hits a terminal criteria. So I'll mention briefly, not the terminal criteria so much, but why this tree in particular is being shown. So on the top right here, you should see what's called the misclassification cost per node. So I want to explain what this plot shows. Um, the vertical axis is essentially error. So how much error is there in the algorithm? It starts off with a fair amount of error, around 25%. So for example, in this first node here, if you just said, okay, I have the data, I'll assume that the outcome is okay, 75% of the time you would be correct. If you just labeled any vehicle as okay, 25% of the time you would be wrong. So that's why there's a 25% 0.25 cost here in this first node. This is just the tree, the first tree, which splits into two terminal nodes. Going across the bottom here is the number of terminal nodes in a tree. Each point here represents a different tree. So the first point is just the top of the tree here. And then as you go to the right in this graph, the tree grows and grows and grows and gets more complex. By the default hyperparameters, that's the parameters that I selected when running this algorithm, it's decided that this point here is the optimal point for a model. But in practice, when you are doing machine learning like this, you might have reasons to look at and select different models. And in Minitab, it's very easy to kind of just switch and look at different trees. I could look at a more complex tree here or a simpler tree. But you can see that the more complicated trees that have like over 10 terminal nodes, so these are huge trees, their performance isn't that much better. At least on the training data, their performance isn't that much better. So definitely this seems like a good tree to use, the problem. Um, so I'm going to show in a second how you actually use this for classification to decide whether a car is okay or not, but I think it's fairly intuitive. You can probably guess just by looking at this how you would use it. But I'm also going to show here how you could try and determine different modes of failure just by looking at this tree. Again, I think that's also quite intuitive. So if we look at the nodes, the terminal nodes that are failure dominant, we can consider how do you get to those nodes. So one possibility, so one outcome here that is dominated by some failed cases is where there's a low level of oil or below a certain threshold within the engine, which would lead to, you could say, an oil failure mode. Or if the oil was above that threshold, but say the airflow in the engine was low, then there's an airflow failure mode or a mode caused by having a low airflow. Or if we look at the other side of the tree, because the only other terminal case on that side of the tree is okay, you can see high temperature and high RPM leading to another failure mode. So that could be overheating. Again, like I don't have personally a great amount of expertise in automobiles. I'm just illustrating with this the idea of how you can read off failure modes from an analysis with a classification tree. And again, I feel like one of the real strengths of decision trees is that they're very human friendly. It's very easy for us as human beings to kind of look at this information um, visually and understand what it's telling us and how we could use it. So, considering how we use it, then I'm going to illustrate how we make a prediction or make a decision given an unknown case. So, so in the middle here, we have a simplified version of that decision tree, and I've just annotated here the numbers for the different variables. So temperature, it was around 216, the oil was around 21, and the airflow is around 9.5, for example. Um, and then we have the decisions that you would make at the different terminal nodes, whether there's a risk of imminent failure or it looks okay. So if we imagine we have data from a new vehicle, from a vehicle, which is, let's say, in use, and we have the values here for the different measurements. So how do we apply this then, or how does the computer apply this to make a decision? Well, first of all, if we follow the tree from the top down, we're looking at the temperature in degrees Fahrenheit, and we're asking, is it less than or greater than 216? The temperature for this vehicle, the engine's running at 201 degrees Fahrenheit. That's below 216, and so we would follow the branch of the tree down to this question about oil level. Um, how is the oil level relative to about 21%? The oil level in this car is 68%, so that's above that threshold. So then we would follow it down to airflow. The airflow in this car is 19 gallons per second. That's above the threshold of 9.5. And so we would conclude that this car is okay. There isn't, there doesn't appear to be an imminent risk of failure or failure within the next few days, for example. So I've illustrated the path through the tree here and the conclusion that it is an okay car. At least for now, the car doesn't have a high risk of failure. I've given another car here, which as you can imagine, is probably not quite the same. But I'll illustrate again the process. So we have a temperature of 211 in the engine. We would follow it down to the oil level question. The oil level is 84 in this car. So we'd follow it down and test the airflow. The airflow is 7 gallons per second. That's less than the threshold here. And so there's a low level of air flowing in the engine. And so the pathway leads us down to a conclusion that there might be it's a high risk of failure in this car. And so we conclude that there's a risk of failure. So this is simply how the model is used and how it would be applied by a machine. One other outcome or one other output that you get from using a model like this is variable importance and relative variable importance. So I won't go into the technical details here. I've underlined the important bit here, which is model improvement when splits are made in the tree. You'll notice that the temperature, though it appeared at the very top of the tree, at the root node, isn't the most important variable with respect to this algorithm, which is using improvement. So basically what this is doing is it's looking at how the purity changed when a variable was used to split the tree. And then whenever a variable is used, it kind of calculates, how useful that is, and then produces a ranking. And the one that's at the top of this ranking in terms of purity improvement gets 100%. So oil happened to be one of the more important variables when it came to changing the purity of the tree. And I think that's largely just due to I had nodes there where there was 100% pure failures, which is pretty extreme. Um, but what you can tell quickly from this is that oil, airflow, engine temperature, and RPM seem to be fairly important variables when it comes to distinguishing cars that are okay from ones that fail. Other variables, tire pressure, the sound, the speed metrics aren't so important. You might be wondering, well, why are these metrics even here when they didn't appear in the tree? That's because there were a lot of other trees and more complicated trees that would eventually use these metrics. But I only picked one that I could kind of fit onto the slide and that made sense for being able to look at failure modes. But that's why these do get some value, but they're significantly less in value compared to the other metrics. So just to summarize at this point, so what I've demonstrated is using automobile data with an AI model, which in this case was a decision tree. So it was a kind of supervised classification model and a machine learning model. And using this model, we could determine if a vehicle appears to be okay in the near future, or if there was some risk of failure within the near future. And furthermore, using a model, and particularly one like a decision tree, you're able to look at the model and we can understand as human beings why an instance is failing or why an instance appears to be okay. I will just mention briefly here before I go on to the final little bit of this talk that I've discussed with some experts, some of our experts in data science about the comparison between decision trees and neural networks. So neural networks are very popular because they can be very accurate and they're also pretty robust at handling features. Um, but one of the disadvantages that's kind of widely known with something like a neural network is that it's what's called a black box function. And that is that it can be very hard to interpret why the machine is making the decision it is when it's doing classification. One of the real strengths of something like a decision tree is it's very clear why decisions are being made. And so they're really good for not just for creating or making the starting point for a model that you could use to kind of make decisions in very complex systems, but it's also good at teaching you. It's like a learning tool that can tell you about like the patterns in complex data and also associations with complex systems if you're able to collect the data in the right format, which is largely what the first part of this presentation was about. So, so I am developing a machine learning methods course, which I wanted to mention briefly at the end of this webinar. And it's largely in conjunction with the predictive analytics module in Minitab. So what I develop in this course is really covering the whole machine learning workflow, which I've illustrated in parts in this talk. So the different kinds of problems and algorithms that we have, and the details of training and of testing. So I didn't really illustrate testing here, but there's a lot of material on like how do you determine how good a model is and ways that you use test data. Another important topic that I didn't really touch on in this webinar is pre-processing. So often in any data analysis task, an awful lot of effort goes into simply the pre-processing. Data is often extremely messy and can be inconsistent when gathered from multiple sites. So a big part of the machine learning pipeline, like applying the algorithm and tweaking it, is usually fairly quick. It's really like doing these pre-processing tasks and getting data into a format that's easy to use and effective and maximizes the accuracy and information you can get from using the algorithm. And then finally, so I just wanted to be fairly brief about this. I do cover a number of algorithms in detail. So I mentioned just cart classification in this webinar, but there's cart regression models, Mars, random forest, and tree nets. And again, these are all implemented as illustrated in the predictive analytics module in Minitab, which I think is a relatively recent addition in Minitab. I think historically it's been a part of Selford systems for a longer time. Yeah. So I'm planning to launch a pilot version of the machine learning methods course later this year. If you're interested, there's a mailing list that you can join to be notified. This will be available in the slides after this talk, so I think Fred will share those. And people who register for the pilot should receive a significant discount for their assistance in helping to kind of figure out the finer details of the course. If there's like too much detail in one area or not enough in the other, like your feedback would be extremely valuable for improving and finalizing the course. So thank you for attending the webinar. So Again, my name's Alexander Bell. I'm a data scientist working for Integral Concepts, and I'll be happy to take any questions you have.
All right. Well, good job, Alex.
Thank
I
you.
think you covered all. Carl posted a handful of questions in the questions tab, but there were more along the lines of pretty much exactly what you were talking about. So there might be a little bit there you see as needing a little more expanse. But if Carl, if you're still on the line, use the chat, and if you have any specific follow-on questions, because I think Carl answered just about everything you did mention in here already. There's a lot of redep defining stuff. So here's one from Shashar right, in the questions tab. How is time variable used in the model, or is it used at all?
In terms of the application of the decision tree, time isn't used at all. So the only point at which time's really being used is when you're collecting the data. So, you're trying to figure out at what point in time to collect data to represent a car that is likely to fail soon versus one that's not likely to fail soon. But then once you've done that, that essentially eliminates time as being a deciding factor there. You're just trying to you're trying to find examples of things that are good, are of one class, and examples of things are of another class, and what tells the difference, if that makes sense. So this isn't a model that uses time to predict failure. Like a lot of, I think, like reliability models are based on time to failure. This is a different way, I think, of thinking about and approaching the problem purely based on examples of something that will fail versus something that won't, if that makes sense.
Let's see, I got
You're
right. So
welcome.
Shir says yes
Yeah.
there, and there's a question from Greg. As of slide 24, I'm embarrassed to confess that's okay. There's a lot of content in this presentation that I forgot. How are the threshold values determined by the tool? Could you jog
Um,
my memory?
yeah. So the full details of this are quite complicated. Like I didn't want, I couldn't go into the full explanation in the webinar, but I'll try to explain. So the key thing is purity. So you have a measure of how pure these split up data sets are. The algorithm prioritize finding the purest data set. So of like you want most of one class in the data you split rather than having mixed up classes. Because, if you imagine taking a data set that's mixed of failed and okay cars, and you split it into mixtures of failed and okay cars, you haven't really got closer to a conclusion as what's okay and what's a failure. Whereas if you can split it into mostly okay cars and mostly failures, that's pretty good. You're getting closer to a point where you can decide. What the algorithm will do is it takes each and every variable. So it'll take temperature, airflow, oil level, etc. And then it will try all the different values in the data, so midpoints in the data as thresholds. And I think that's, yeah, your question is how are the threshold values determined? The actual values are between the data values. So if for all of the data you have, for example, temperature in degrees Fahrenheit recorded, it tries each value between those temperatures. It's each point where you could split the data, if you see, when you've ordered the temperatures.
So
So that
it's a little more sophisticated, I think, but it just simplistically, it's a ranges from 150 to 250 degrees. It starts at 200 and says, "What's the split?" And I go up 5 degrees, and it says, "Well, that's better. Let me follow that." Or I try them all and see which one's best. Or
So specifically, it uses values between the actual data values for temperature, because those are the points at which we'll actually split the data, if that makes sense.
right, right, yeah. So instead of picking a random number on the variable, it just picks. I have 100 data points, and it picks
Hmm.
one and says, "All right, how's that split it?"
Yeah, yeah. But specifically, it's the point between data points. So, for
Okay,
example, if you had a temperature like 200 and 201 for a couple of data points, it'll use 200.5 as a
okay.
split, as a threshold, because that actually splits the points.
But it
And then,
basically can just try a whole pile of them and say, all right,
yep.
this is the cleanest split that this provides.
Yes.
And
Yeah.
that's good enough. Move on.
Based on purity. So
Yeah.
it's got a measure of purity. It's a cost function or a profit function, if you like, and it just optimizes on that function. It finds what creates the purest average split.
Okay.
Yeah.
There's another question here from Alex. Alex, I'm trying to not say your name instead of
Benson.
yeah, from Benson. Let's go last name. Yeah.
Yeah.
Uh, should we understand this classification method as instantaneous diagnostics?
What is instantaneous diagnostics?
Well,
Do you?
just by straight line definition, I would say is you're looking at this car is showing
Hmm.
this set of 8 variable readings
Hmm.
right now.
Yep.
And then given that data independent from its history. So it's
Yep.
not counting that
Oh,
oil pressure is going up
yes.
or temperature
Yeah.
is
Yeah.
changing or whatever.
Yeah. Yeah. Absolutely. Yeah. I think that does. It is instantaneous diagnostics then. It's based purely on just a set of data that you give at a time point.
So in this case, in a practical sense, you could
Mm.
alert, here's another app for the App Store, I guess, but or an
Yeah.
oil light that we'd ignore on our dashboard. It says, "Hey, this is something's going wrong. You got to go to the shop."
Yeah,
In
that's
a
something that,
practical sense,
yeah. Yeah, that's something I had in mind for like how this kind of approach can be applied.
okay. But
Yeah.
what if, like, on my way to the shop, that light goes out because I'm driving slower and there's a lower temperature?
The light, yeah, so I think there's a lot of details that would have to be handled in the actual, like the practical application of this software, of this process. So what I presented in the webinar is a gross oversimplification of I think a very complicated, what would be a very complicated problem.
Yeah.
But I think it does provide a good starting point as something that, for example, engineers could use to then tweak and make practical. Um, is what I'd say. Because again, I'm not an expert on automobiles. I know that having low oil is bad for the engine, for example, but I don't know. I was just coming up with an example that kind of illustrates more the idea and how machine learning works and how machine learning is used to approach the problem. But yeah, in
Okay.
terms
So
of like how you'd handle changes over time, like you were saying, the temperature changes, that might be something that you put alongside or in parallel to the model. Yeah.
okay. Yeah. So if anybody wants to go implement this as the next $1 million idea, good luck to you.
Mhm.
The example is an example. All right. Let's see. Greg asked, so Minitab used its carts routine. And I think I can answer that is that, yeah, you did. You talked about you're illustrating the cart routine in Minitab
Hmm.
and some of the outputs. All right. Steve's going to check his car to see if it's
Yeah.
going to make it to the airport, I guess. Well, if you check it while it's still cool, you'll be in pretty good shape. All right. See, any other questions? I'm monitoring. Let's see. I'm not seeing anything new in the questions tab or wherever. And I did add the link to I'm interested in the upcoming course.
Thank you.
Let me try that again. This is a break from our typical webinar practice. We usually don't, add an ad at the end of it, but we'll see how it does. But it's obvious there's a whole lot more to this than
Hmm.
just hit Minitab and go at it blind.
Oh yes. No, I do put a lot of detail into the course of the various stages as mentioned. And I think you're sharing the slides and stuff after this. But I'd be perfectly happy to prepare another talk at some point in the future on a different aspect, perhaps a machine learning, perhaps the regression problem.
Yeah,
Hmm.
those are life of motors. Yeah, that's great.
Yeah.
And Steve, well, I don't know. So Alex, how's the recording going?
Sorry?
How's the
The
recording
recording's
of the course going?
it's going well. I'm over 70% of the way through finalizing the material. That's the content. And then I think the recording should go pretty quickly afterwards. I saw Steve mentioned the pilot. So yeah, the pilot will be online, so all of the content will be recorded and on demand. Yeah,
And
it's
you're
not a
available
lot.
to, and then you're available to answer questions and like
Absolutely.
all the courses that we have behind the
Yeah.
scenes with Steve.
Yeah, and through the slides, people should have my email, so definitely feel free to email me with any questions about this webinar or about the course. I'd be, very happy to respond.
Yeah. All right, cool. All right. Well,
Mm.
I'm not seeing any other questions. A few thanks coming in. So people are heading off to the rest of their day. And did you know, as a complete aside, I saw a note yesterday that yesterday was National Nap Day because it's the first Monday after the time change. My cat was ready for me to go take a nap with her yesterday. But,
Oh, mm.
all right, looks like we're getting a bunch of thanks. All right, thanks so much, Alex.
Yeah,
And I look
thank you.
forward to chatting some more about this. Yeah, every day should be nap day. I get that, Christopher. All right. Thanks so much, everybody. We'll wrap this up and I'll get the recordings posted as soon as I can, probably a day or two. And then we'll go from there. All right. Thanks, Alex. Talk to you later.
Thank you. Yeah, see you. See you, everyone.